Okay, gentlemen, I'm going to go over the solutions for topic 9.3. This is the second interference handout. There are a couple of things that we need to take note of. First, for diffraction gratings, our conversion factor for distance is going to look something like this. 1 divided by d is equal to the number of lines per distance. So a lot of problems are giving you these diffraction gratings with, for example, 200 lines per millimeter, right? So we can take that and convert it to the distance that we need for our formula in the data booklet. So this will give d is equal to the number of lines divided by distance to the -1 power, and we do need to convert that distance to meters. So let's see what that looks like. Here for number 33, we're asked to calculate the angle to the normal of the third order maximum. So if we zoom in here, you can see our wavelength is 460 times 10 to the -9 meters. D then will be given by 200 lines per millimeter. And you can see here that I've converted millimeters to meters using the conversion factor. And then we multiply this entire expression by the exponent, we raise it to the exponent -1. And that will give us a distance of 5.0 times 10 to the -6 meters, which we need. Here we have a very small angle. So we can use a small angle approximation, and that is okay. Our third order maxima is going to be given by then our angle multiplied by 3, and we then need to convert that to degrees just to match the answer given by our solutions, which I don't have on this page, but the solution is given as 16 degrees, so we convert radians to degrees, and there you go. Some of you may be asking yourselves right now, do I normally need to give my answer in degrees? And the answer to that question is, it should be specified by the problem. This one is not specifying it, so I'm not sure why they give it in degrees. Okay, next problem. A diffraction grating is used with monochromatic light of 6.3 times 10 to -7 meters, and a screen is placed at a perpendicular distance of 3.75 meters away. How many lines per millimeter are there on the diffraction grating if it produces a second order maximum 38 centimeters from the center of the pattern? Okay, so first thing we do is define our variables. Okay, so here I've got wavelength, I have the distance to the screen, I have the distance to the second order maxima, 0.38 meters, and the second order maximum tells us that n is equal to 2. That is what second order is indicating. Okay, we then rearrange this equation here slightly, so that we have d is equal to n times wavelength times the distance to the screen divided by the distance to our second order maximum. And we plug in our values, and we find that d is equal to 1.24 times 10 to the -5 meters. And we then need to convert meters to millimeters because that is what our question is asking for. How many lines per millimeter are there on the diffraction grating? Okay, so we then find that d is equal to 1.24 times 10 to the -2 millimeters. All right, if we have that information, we can then convert that to lines per, this should say lines per millimeter, or just line per distance, really. Okay, so lines per distance will be equal to 1 line divided by d. And when I plug in my value for D, I will find that my diffraction grating has about 80 lines per millimeter. Okay? So there you go. There is number 34. So number 35, the issue with number 35 is you cannot use a small angle approximation here. So if you calculate your angles, trying to use a small angle approximation, they're just too big for your approximation to be good. Remember, the bigger that angle gets, the worse your approximation is. Okay? So here, as you can see, I've once again defined my variables, wavelength and 1 divided by D. And 1 divided by D gives me the number of lines per millimeter. And I then convert that value, this, to D, and convert it to meters. And I'll find that I have 1.3 times 10 to the negative 6 meters. And this seems to be a pretty common scale for D, okay? So just make a note that if you get an answer that is way, way bigger or way, way smaller than this, you may want to double check your math. Okay, not using a small angle approximation, I will find that my angle to the second order maxima, yeah, we're using a diffraction grating, so it must be a maxima. So my angle to the second order maxima is 0.919 radians. I've just plugged the values in here. I don't have a lot of space, so I didn't actually plug these values in, but hopefully you get the idea. Using that angle then, and using the radius as 1.8 meters, I will find that my second order maxima is 2.359 meters away. And that's a pretty big value, right? So that's why our angle is large. Okay, we then go through the same process for the angle to our first order maxima, and we will find that that is about 0.78 meters. Okay, I then take the difference between those two, and that gives me 1.6 meters, which is quite large, particularly relative to the distance to the screen, right? 1.8 meters. So, yep, no small angle approximations. They're not going to work. Okay, which I've pointed out here. 36. 36 gets a little bit tricky, and so let's take a look. So, teacher is using a diffraction grating of 300 lines per millimeter to show a class of white light spectrum. So she wants the first order spectrum to be 10 centimeters wide. Okay, so what we're looking at here is a situation where we're going to produce multiple spectra. Okay. So in order to do that, we need to look at the wavelengths at each end of the spectrum. Okay, so we need the wavelengths for the visible spectrum of light, and we need an upper boundary and a lower boundary. So the upper boundary is given by 700 nanometers here, and the lower boundary is given by 400 nanometers. Okay, we are given D in the form of the number of lines per millimeter, and here you can see I've converted D then to meters. And we also know that delta S, which is going to be S1 minus S2, is equal to 0.1 meters. Okay, that's defined in the problem. Remember, we want that spectrum to be 10 centimeters wide. Okay, so delta S will be S1 minus S2 minus S1. As I stated previously, we know that our wavelengths are given by 400 and 700 nanometers. Okay, so here I've just written the math. Change in S is equal to S, the value for S1 minus the value for, the value for S2 minus the value for S1, where this is the value for S1 and this is the value for S2. Flip that backward. This is S sub 2 minus S sub 1, okay? Okay, so then I do a little bit of factoring just because I don't like duplicating math if I don't have to, and I'm eventually going to have to plug all this into a calculator, so it's a bit of a time saver. I then will solve my, I will then solve this equation for D, the distance to the screen. And once I have that equation, then I just plug in my values and I will find that the distance to the screen should be 1.1 meters, which matches the answer given. Okay, so as you can see, this is kind of not trivial, but a very interesting question. All right, I'm going to stop the recording here. If you have any additional questions, please do not hesitate to let me know, and have a fantastic day.